So in this video, we're going to talk about why we use ordinary least squares. So I'm going to go over here. So here you can see that we use we're using ordinary least squares to estimate our coefficients. So here we'll go over why. So this is the curve fitting and loss functions file on eCampus. We'll run it. We're using seed 77. So this way we'll all have the same numbers. And for this, I'm estimating, or I'm generating data based on this function here. So it's a polynomial, second degree polynomial plus noise, and the noise has a mean of 0 and a standard deviation of 2.5. So here's our function. You can see that it does kind of have that polynomial shape, has that has the hump up at top. So we use ordinary least squares. This is the math behind it, or not necessarily the math, but code that would also generate it. You don't need to calculate all that. But what I'm doing here is I am estimating so many curves to try to fit it. So I'm using the math behind the polynomial fit ordinary least squares to just keep fitting lines over this. So the straight line, this is the mean. This is the 0 degree. So it's just one point estimate, just one number that best describes it. So at any time, at any point on this line, it is the mean, and that is the number that you're using to describe it. Then on here, this line going down, that is a second degree. And as you can see, as you add more and more degrees to the polynomial, it is a better fit, or it's almost exactly fit. It's almost an exact fit, but it's overfit. You can see that even though for the 5th and 6th degree polynomial, it intercepts every single time. You can't use this to estimate or to extrapolate any information. You can't even use it to interpolate anything in the middle, because it's going through each one, but it's not flexible enough. So for this, let's use ordinary least squares. So the way ordinary least squares works, so why we want to use ordinary least squares, it is based on the mean. So if we have a point estimate, it's found if we just have one number that best describes a data set or a column or a series of data, and we use ordinary least squares and we just use it to estimate one number, the constant, that would be the mean. So then we add another variable. Now we have x included, and x is now based on x. That now we have the constant. We have two coefficients. We have the intercept and the slope of x. So now it's their expected value of y conditional on x. And here is our regression parameters. If we run it again, this time we use x squared. So now it's the 1's, x, and then x squared. Now we can see that it is a little bit of a better fit. It's not a perfect fit. It's not a perfect fit. And even here, it's not all, just judging by some of this, it's not all the best fit. But we get the regression parameters, and we can see that it is reasonably close. Remember, our y coefficients, it was 10. So it's 10 plus 2x minus 0.25x squared. And we're relatively close. We get 11.08 plus 1.65x minus 0.23x squared. We're relatively close. We're not that far off. Then if we continue, this is be the bad regression. So this is the bad regression. We even named it bad regression. I'm going to print instead of just showing that way. It looks a little bit cleaner. Here we have a much better R squared than before. So this, whenever you, make sure you read chapters 2 and 3 of the book. But based on those chapters, even then, it will say that just going by R squared and the residual squared alone is not necessarily a good thing. So we've overfitted. So even though, judging by some of these statistics or these values, this would appear to be the better model, but it's overfit. You can't, even though the results, the regression results appear to be such a better fit, you can't use this to estimate or predict anything in the data, because it's overfit. You can see that if you were to say what's y conditional on x being 12, you would get a number way up here, but in reality it should be down here. It should be possibly even a negative number. But if you use the 5th degree or 6th degree polynomial, you're going to get a large jump in value. It'd be significantly off. So how does all of this work? Comparing the coefficients. So the way ordinary least squares works, it does it by trying to minimize the mean squared error. So these are our loss functions. So here's our data. If we have our if we want to estimate ordinary least squares coefficients, we're going to do that by minimizing our mean squared error. So this is this should be familiar if you've had an econometrics class. If not, it's fine. But ordinary least squares is found by minimizing the mean squared error. So these are loss functions. They measure the errors of the function that we're estimating. So mean absolute error. This is this uses absolute error. So and then a point estimator that minimizes. So if you were going to use one number that best minimizes mean absolute error, it would be the median. It's right in the middle. And that makes sense because it uses the absolute value. For mean squared error, which is what you use in econometrics, for a point estimator to minimize this, it would be the mean. And one of the reasons why we like mean squared error is that it is linear in coefficient. So with this, with the mean absolute error, this is not a linear function or not linear in coefficients. You would have a stop. But with this, this would be linear. So you can take derivatives and things like that a little bit easier. And then for another loss function, common loss function is root mean squared error, which is just a square root of MSE. So let's actually go over some of the math. And again, we won't go over any of the derivations. We're just going to kind of show it to visualize. So with this is a function for MAE. So it's the mean absolute error. And then we're going to plug in coefficients. So we want to minimize mean absolute error. Here is another one, mean squared error. We will want to minimize that. So here, based on this, so this would be the actual coefficients for the function. So 10 and 10 plus 2x minus 0.28 or 25x squared. So for the original function, the mean absolute error is 1.64, the mean squared error is 4.63, and the root mean squared error is 2.15. And then why we take the root, the mean squared error is going to be in units squared, like variance. This would be kind of like variance. It's in units squared, whereas root mean squared error gets it back into the original unit. So if this was time, mean squared error would be time squared. Root mean squared error would just be in time. Then to show it, so now we're going to use the SciPy optimize function, or so we're to minimize it. So we're minimizing means absolute error, and we get 10.56 and so on. And this isn't too far off. It's not significantly off on the compared to the original coefficients. So the original function. And if we plug that in, or we estimate the mean absolute error, we get 1.63. So this is pretty close to what the actual coefficients would give, but it is a little bit better. So we have a lower mean absolute error than up here. But still, this is not necessarily a better function. Then we'll do it again, but this time we'll minimize the mean squared error. We get 11.08, 1.65, -23. So this is a little bit better. It's not necessarily close. So let's look at the mean squared error for this. Mean squared error, we get 4.05, whereas the mean squared error for the original would be 4.62. So this is actually a lower mean squared error than before. Now let's look at the reg parameters. So this is from the other regression. This is from the ordinary least squares regression from before. So if I do, if we print the regression summary, so reg.summary, open, close for another parentheses. I think I have too many R's. We have the same coefficients, so 11.08 and so on. this is the same result. These are the same coefficients that you get in the mean squared error by minimizing mean squared error. So there's a lot of math involved. That would be more for an econometrics class where you get into the derivations, or maybe a regression analysis class where you get into the derivations of why or where these numbers come from and the process behind it. But mainly just know that for ordinary least squares, you get it by minimizing mean squared error. And why this is important, I'm going to just keep going a little bit further. Remember, for mean squared error, a one number, if you minimize mean squared error and you want one number that best estimates the data, you're always going to get the mean. And you can see that the mean goes right in the middle of the data. Whereas if you use mean absolute error, you get the median. If you just want one number that best describes it, you get the median. And you see it's a little bit higher. It's a little bit upwardly biased. So the median is not as good of an estimate as the mean. So by using ordinary least squares, you can take that step further. And by using ordinary least squares, we minimize the mean squared error, which goes right in the middle of all of the data. And it's relatively close to the actual function. You can see the mean absolute error is upwardly biased. It overestimates, which is consistent with the median. The median in this specific case is greater than the mean. So by using mean absolute error or another algorithm to estimate these coefficients, you're going to be biased and you're going to be off. It's not going to go right in the middle of the data. So ordinary least squares in most cases is always going to be better. If you're just doing a simple linear estimation, or you're trying to estimate coefficients for a linear function, ordinary least squares is always going to be better. It goes right through the middle. This is why it's so commonly used, and why it's so important. So it goes right in the middle because it uses the mean. So it's right in the middle of all the data, and it's close to the actual. Whereas the median is upwardly biased. And then for this, if you take this another step further, in the book, in page 39, you have interpretability versus flexibility. So with this, you have least squares right here. So this is ordinary least squares, what you commonly use in econometrics. And from there, you can get you can have more flexibility. Maybe you have more predictability with GAM or boosting or support vector machines, but they're not as interpretable. One of the things that makes ordinary least squares nice is that it's easy to interpret. It's linear in coefficients. It's linear in the parameters. So it's easy to interpret. It's easy to take derivatives. It's easy to see relationships in ordinary least squares, whereas something a little bit more complicated, such as support vector machines, it's harder to interpret. It's harder to have inference on the data or inference on the relationships within the data. So this is why we use ordinary least squares for our algorithm to find the coefficients, or why this is a better method, I should say, to find the coefficients. So in the next video, we'll continue with regression analysis, and we'll talk about forward selection, backward selection, and mixed, which comes from the book.